The IMO announced the 2018 initial GHG strategy as part of efforts to strengthen global carbon emission regulations. Under these GHG reduction goals, the aim is to reduce carbon intensity by 40% by 2030 and 70% by 2050, compared to 2008 levels, and to cut total greenhouse gas emissions by 50% by 2050. On the technical side, the EEXI Energy Efficiency Existing Ship Index regulation has been in effect since 2023 for international vessels of 400 gross tons and above. On the operational side, the CII Carbon Intensity Indicator regulation has been in effect since 2023 for international vessels of 5,000 gross tons and above. For existing ships with internal combustion engines, meeting carbon regulations will require the use of low-carbon fuels or the adoption of carbon capture technologies. Cryogenic carbon capture, or CCC, is an advanced technology that captures CO2 from exhaust gases by directly converting it from vapor to solid at ultra-low temperatures, without the use of chemical solvents. Unlike conventional CO2 capture methods, CCC enables one-step, simultaneous solid-phase separation without CO2 liquefaction. This results in a more compact system and significantly lower energy consumption. When combined with heat recovery, total energy use can be reduced to as low as 500 kilowatt-hours per ton of CO2. Its modular cold box can be reused at any site where CO2 concentration is consistent, regardless of oxygen or nitrogen levels, allowing for flexible and cost-effective operation. The compact design also enables quick installation, reducing both construction time and costs. CCC is also compatible with a wide range of CO2 concentrations and is expected to achieve capture with energy consumption as low as 1 gigajoule per ton of CO2. Cryogenic carbon capture. Flue gas compression and water removal. Flue gas compression. After cooling or heat recovery, the engine exhaust gas is compressed by a centrifugal compressor to approximately 3.5 to 5.5 bar. Water removal. The moisture in the compressor outlet is controlled to below 10 parts per million before being fed to the cold box. Flue gas recompression and cooling. Flue gas recompression. The energy generated from the expansion of the CO2-free flue gas is used to compress the cooled flue gas containing CO2 at ambient temperature to above 6.5 bar. Heat exchange and recuperation. Shell and plate heat exchanger 1. The residual cooling energy of the final discharged gas is utilized to cool the flue gas down to its dew point. Heat exchange and recuperation. Dry flue gas is cooled to below -60 degrees Celsius in a two-stage heat exchanger, with its sensible heat absorbed by CO2-free clean gas to achieve the cooling. Nozzle expansion and phase change. Phase change nozzle. As the gas passes through the nozzle, its temperature drops rapidly, causing CO2 to undergo a phase transition into solid dry ice. Solid CO2 capture process. Gas-solid separation. The solid phase CO2 is separated from the gas phase N2/O2, with the solid CO2 discharged downward and the gases vented upward. Compression and expansion. Gas phase N2 and O2 expand in the expansion section, and the work generated by this expansion is used to drive the compression section. Solid CO2. Transition process to liquid CO2. Solid CO2 transition. The solid CO2 fed from the top is enclosed in a transition chamber, and upon heating, it undergoes a melting process and transitions into the liquid phase. CO2 clean gas heat exchange process. Heat exchange and recuperation. The cold energy from the expansion of the CO2-free clean gas is used to cool the gas entering the cold box. The Institute for Advanced Engineering and Sunbow Industries are jointly operating a cryogenic carbon capture demonstration plant with a capacity of 12 tons per day. Using a flue gas system that produces exhaust with up to 15% CO2 concentration, the plant has achieved a capture efficiency of 94.7%. They now aim to validate long-term operational reliability and structural integrity, paving the way for full-scale demonstration aboard ships.